Hi team, thank you for joining me again for another APES screencast. In this screencast, we're going to start chapter 13 and talk about water resources. Access to fresh water is essential for our survival and maintaining our lifestyles, and the Colorado River is a great example of that. The Colorado River flows through 7 states and includes 14 dams and reservoirs, including the Glen Canyon Dam, shown here on the left side, located on the border between Utah and Arizona. These dams and reservoirs store water and generate hydroelectric power. The Colorado River supplies water and electricity for about 30 million people in the Las Vegas, Los Angeles, and San Diego areas. Finally, the Colorado River provides the water to irrigate the crops that feed much of America. This diagram shows the path of the Colorado River from the Rocky Mountains in Colorado to the Gulf of California in Mexico. It also shows the dams that have been built along the course of the river. Unfortunately, our dependence on the Colorado River has created environmental issues. First off, very little water is actually making its way to the end of the river at the Gulf of California. Secondly, the current rate of water withdrawal from the river is unsustainable. And finally, much of the water used for agriculture is used inefficiently, thus being wasted. The photograph on the left shows the Hoover Dam and its historical high water mark and how drought and water withdrawals have lowered the level of the water. On the right side, you have a man hiking the end of the Colorado River with no water flow to be seen. Since 2014, there have been efforts to release water from dams and reservoirs to restore flow all the way to the end of the river. This is a photograph of the Colorado River Delta, where the Colorado River meets the Gulf of California. This is another photograph of the Glen Canyon Dam, showing the Lake Powell Reservoir behind it. The dam and the reservoir store water and generate electricity. In section 13.1, we're going to talk about our supplies of usable water and whether or not these supplies are going to last us into the future. The first thing we need to understand is that most of the Earth's fresh water is not available to us. Only about 3% of all water on Earth is fresh water. Unfortunately for us, most of that fresh water is frozen. 0.024% of all water on Earth is available liquid fresh water, underground in the form of groundwater and above ground in lakes, rivers, and streams. This diagram emphasizes the minuscule amount of all water on Earth that is available to us as liquid fresh water. This diagram shows the relative amount of all water on Earth, all fresh water, and all fresh water in lakes and rivers in comparison to the volume of the Earth itself. The availability of fresh water on Earth is driven by the hydrologic or water cycle. The hydrologic cycle is powered by solar energy and gravity. Solar energy powers processes like evaporation, transpiration, and the transport of moisture in the air. Gravity allows water to move from one place to another. Human activity can alter the hydrologic cycle and thus the availability of fresh water. We can do things like withdraw water from the ground, pollute bodies of water, and accelerate climate change. This is a diagram of the hydrologic or water cycle. Please be familiar with all the terms you see in this diagram. You may be unfamiliar with terms like transpiration, the loss of water from plants, infiltration, the movement of water into the ground, percolation, the filtering of water through the earth, and through flow, the flowing of water underground. This diagram shows mean annual precipitation around the world. It shows that freshwater availability differs from place to place on Earth. Groundwater is a critical freshwater resource. Groundwater can be found in aquifers, underground layers of water-bearing rock. Underground, you'll have a zone of saturation where spaces between soil particles are filled with water. The upper boundary of the zone of saturation is called the water table. The water table is also the boundary between the zone of saturation, saturated with water, and the zone of aeration, where the spaces between soil particles are filled with air. Groundwater accumulates and restores itself through a process called aquifer recharge. There are two ways in which this can happen. In natural recharge, water infiltrates the ground and percolates downward through the soil. In lateral recharge, water filters sideways from streams and rivers. In addition to groundwater, another critical source of fresh water is surface water. Surface water is water above the ground, and it comes from surface runoff that comes from a watershed or drainage basin and accumulates in a body of water like a river, lake, or stream. We cannot collect, depend on, and use every drop of water that falls to the Earth's surface. We use the term reliable runoff to refer to all surface runoff that we can depend on and calculate on a regular basis. Only about 1/3 of surface runoff is considered reliable runoff. Around the world, 10% of the water that we use is used for domestic purposes. 70% is used for agriculture and 20% is used for industry. In 2017, Hurricane Harvey flooded parts of Texas and Louisiana. Floodwater is difficult to collect and cannot be depended on. As a result, floodwater is not considered reliable runoff. If you look at how much water the individual person uses, we call this his, her, or their water footprint. Agriculture accounts for 92% of humanity's water footprint. When we measure the water footprint, we have to take into account virtual water. This is water that is not directly consumed, but is used to produce food or other products. For example, it takes about 200 liters of water to produce 1 glass of milk, or 70 liters of water to produce 1 apple. This table lists how many bathtubs full of water it takes to produce these common items. If we look at freshwater resources here in the United States, we see that we have more than enough renewable fresh water. We also see that most water in the United States is used for cooling in electric power plants. The nuclear power plant pictured on the right here is releasing steam and condensed water rather than smoke. In the United States, we also see that fresh water is unevenly distributed and polluted. Climate change models project prolonged drought in the southwestern United States, including here in California. In 2007, the United States Geological Survey identified water hotspots, or potential areas of conflict over water. In the photograph on this slide, you can see the bathtub being filled with polluted water in Flint, Michigan. This map shows areas in the western United States with water conflict potential and rural areas with unmet water needs. It is feared that freshwater shortages will only grow in the future. A 2010 United Nations report found that by 2025, about 3 billion people around the world will lack access to clean water because of things like drought, overpopulation, and water waste. This is a map of areas in the world that are likely to experience stress from shortages of fresh water. This is a map showing areas of the world where people don't have access to clean or improved drinking water sources in green, yellow, and red. There are ways in which we can increase freshwater supplies where they're lacking. First, we need to collect accurate information about water supplies and potential shortages. Then, we can increase freshwater supplies by withdrawing groundwater, building dams and reservoirs, transporting surface water, or converting salt water to fresh water. In section 13.2, we're going to consider whether or not groundwater is a sustainable resource. Most aquifers are renewable unless they are contaminated or overpumped. Aquifers provide drinking water for about half the world. Unfortunately, water tables are falling in many parts of the world, primarily due to crop irrigation. This infographic lists both the advantages and disadvantages of using groundwater as a source of fresh water. The Ogallala Aquifer is a good example of what happens when you have a renewable resource that isn't given time to renew itself. The Ogallala Aquifer is the largest known aquifer in the world. It irrigates the croplands of the Great Plains. Unfortunately, it's being overpumped at a rate that is 10 to 40 times faster than it can recharge itself. Government subsidies are incentivizing farming and, as a result, incentivizing the rate at which the aquifer is depleted. Scientific studies have shown that biodiversity has been threatened in some areas above the aquifer. This map shows areas of the United States where groundwater overdraft is high or moderate. It also shows water level changes in the Ogallala Aquifer in meters. Overpumping aquifers can have several harmful effects. First, it can limit future food production by limiting future water availability. Second, it can hurt small farmers who can't afford to pump deeper for water. And third, it can cause land subsidence or sinking. This can be seen in Mexico City or the San Joaquin Valley of California. In these photos, you can see the tilting and buckling of buildings due to land subsidence in Mexico City. In this photograph, taken in the San Joaquin Valley of California, you can see land subsidence between 1925 and 1977 caused by overpumping of groundwater in aquifers. Overpumping can also cause sinkholes or the collapse of underground caverns drained of groundwater. A sinkhole is shown in the photograph here. Overpumping can also cause saltwater intrusion, where saltwater replaces overpumped freshwater in coastal regions. This diagram shows how saltwater intrusion works. As freshwater is diverted and pumped from the ground, saltwater moves further and further inland. This infographic lists ways in which we can prevent and control groundwater depletion. Another way in which we can address freshwater shortages is by tapping into deep aquifers. Deep aquifers are deeper than normal aquifers and are often confined between layers of rock. They have the potential of providing billions of people with water for centuries. There are concerns with using deep aquifers, though. First, they're non-renewable. They will take centuries, millennia, or more to recharge. Secondly, they can flow beneath more than one country, raising ownership issues. And finally, the cost of tapping them is unknown and could be very high.